Hello, and in the final one of these videos, I want to talk about slew rates in op-amps. The slew rate is the maximum rate at which the output of an op-amp can change. You can think of it as arising from this model of an op-amp, the one we used to derive the bandwidth of op-amps and op-amp amplifiers. A current source here, which is related to the difference between the input voltages, driving a capacitor and a resistor. But that current source has a maximum possible value, which means that this capacitor here has a maximum rate at which it can charge up. And that means that the rate of change of the voltage across this resistor has a maximum value, and therefore the rate of change of the output voltage has a maximum value as well. If you wire up a circuit with an op-amp and suddenly change its input voltage, you'll see the effect of slew rates on the output. The output voltage doesn't suddenly jump from one value to its new value. It takes some time to get up to its new value, and it tends to move in approximately straight lines between the old value and the new value. And that's because that little capacitor inside the op-amp is charging at its maximum rate in order to try and get the output to its new stable value. There's a common and interesting calculation that can be done with slew rates, and that is to work out the maximum frequency at which a sine wave can be output by the op-amp in an undistorted form. And the calculation goes like this. Supposing I had a voltage that I wanted to get out of my op-amp, V out, the function of time, which was A times sine of omega t. In fact, in the slide I've defined A as being a peak-to-peak amplitude, so let's use the same terminology here and say that my voltage at my output is A over 2 times sine omega t, which is a variation from minus A over 2 to plus A over 2, so has a peak-to-peak value of A. Then, the rate of change of the output is just going to be A over 2 times omega cosine omega t. Now, if I'm going to have an undistorted sine wave in my output, then my op-amp has to be able to change its output at this rate. So this has to be less than the slew rate of the op-amp. And it has to be less than the slew rate at all times. Well, the maximum value of cosine omega t is 1. So the biggest value that this term here can ever have is A over 2 times omega. In other words, A omega over 2 has got to be less than the slew rate. Or to put it another way, A has got to be less than 2 times the slew rate divided by omega. Now, typically we tend to use hertz as units of frequency rather than radians per second when we're designing op-amp circuits. So we could use the fact that omega is 2 pi times the same frequency in hertz and write this as A is less than 2 times the slew rate divided by 2 pi f. The 2's cancel, and we just end up with the formula that we have in the slide. A is less than the slew rate divided by pi times the frequency in hertz. And that's the maximum amplitude of signal that you can have at frequency f in order for the output of the op-amp not to be distorted. And if you're dealing with high precision signals, that can be a limiting factor on how fast and how big the signals are that you can process. If you look at some typical values for the slew rates of op-amps, you'll see that for most of the op-amps that we're using in this module, the slew rate is around about 0.5 volts per microsecond. That's the typical units in which slew rates are quoted. It doesn't make that much sense to say that the slew rate is 500,000 volts per second, because you're never going to get an op-amp which can have an output swing of 500,000 volts. So, 0.5 volts per microsecond or so. It's not usually a problem at audio frequencies, but as we get towards higher frequencies, it can be something that can limit the large signal behaviour at high frequencies of op-amp circuits. And that brings us to the end of this short series of videos about non-ideal op-amps.